Hi, everyone, and welcome to another Geo-Institute live stream. My name is Christina Scott. I am the Senior Technical Manager at the Geo-Institute, and it's a pleasure for me to be here with you today. Before we go to our moderator and our presenter, I want to mention a little bit about what's about us, about the Geo-Institute. If you know, we are a technical society with over 12,000 members, and we are part of the American Society of Civil Engineers. If you want to know more about the Geo-Institute, go to the geoinstitute.org website, and you will find there that we have technical committees, we have board committees, we have chapters all around the nation, and other little committees involving students. Before we continue moving forward, I would like to remind you that you can get your own raw pet bobblehead. You just need to go to the Geo-Institute website, and there in a corner we have the Student Participation Fund. And with a donation of $96 or more, you can get your own raw pet bobblehead. All right, now moving to our business. I would like to introduce Leela Krishna, a grad student at the Texas A&M University. Leela, if you're ready, the floor is yours.
Thank you. Good afternoon, everyone. Like Krishna said, I'm Leela Krishna Mohan from Texas A&M University. I'm really excited to introduce Dr. Richard, Professor Emeritus of Civil Engineering at Royal Military College of Canada and also with the Queen's University. He was a past president for several major engineering societies and has published more than 230 journal papers. And his impact is on geotechnical engineering is felt worldwide. His research has shaped how we understand design of reinforced soil structures from walls to seismic performance and much more. Right now, he's also serving as editor-in-chief of two leading journals, and is currently ASCE Geo-Institute Cross USA Lecturer for 2024-2025. I now introduce Dr. Richard Bathurst. He will be introducing more about himself and delivering the talk. Over to you, Dr. Richard.
Thank you, Leela and Dr. Bathurst. My apologies. We have a sponsor for this live stream, so I would like to shout out our sponsor, GeoPeer, and I would like to share their video about their services. My apologies on that. Ooh, where is my video? Okay, let me stop sharing again. I need to share the voice. Okay. Thank you, GeoPeer, for sponsoring another Cross USA lecture. Now, Dr. Bathurst, the floor is yours.
Okay, I'm sharing my screen. Can you see my screen? I think you can. Just a moment.
Yes.
I'm just trying to get the full screen to you.
Okay.
How is that?
Looking good.
Okay, so you can see my entire screen? Good. So thank you very much, Leela and Christina, and many thanks to the Geo-Institute for this opportunity to deliver this third and final webinar as part of my 2024-25 Geo-Institute Across USA Lecture Tour. And the topic of my presentation is Analytical and Numerical Modeling of the Reinforced Fill over a Void Problem, considering rate-dependent geosynthetic stiffness. That's quite a mouthful. All right, I'd like to start immediately by giving a shout out to my former PhD student, Fahima Nafchali, who graduated about 2 years ago. She's the one that did all the heavy lifting and the work that I'm going to show in this presentation. So let's introduce the general problem, which is the problem of a reinforced fill over a void or a sinkhole or a cavity. So the scenario is that we want to be able to support a fill that has collapsed over a void or a sinkhole long enough that we can remediate or fill the cavity and reinstate whatever surface structure has been damaged. And so this geogrid that you see, for example, in the bottom left-hand photograph is placed at the time of construction of the fill. And it will support the fill layer until remediation can take place. And so the question that we need to answer is, how can we select an appropriate geosynthetic reinforcement, for example, a geogrid, in order to provide this support prior to remediation? And there are, in the literature, a number of analytical solutions for this problem. And these approaches can be found in the references that I show you here. The seminal publication was by J.P. Giroux and his collaborators that you see at the top. And basically, modifications to the general approach have appeared since. And some of these analytical solutions can be found in codes in Europe, including Germany and the United Kingdom. I'm going to, by way of introduction, give an example of the British code. And these codes, what we have done, and these methods, what we have done, we looked at each one of them, and we provided a design chart approach to solve the general problem. And this is what you can see on your screen here for the British approach. So one starts at the top figure with an assumed allowable strain in the reinforcement, and this will define the ratio of the deflection, the vertical deflection at the base of the reinforcement to the width of the void. So one comes across this chart, and you can relate the geometry of the deformation, if you like, to the allowable strain. And here you see the equation. You know, typically we like to keep the strain in the reinforcement to 5% or less. And if you have a strain that's greater than an allowable value, you can calculate a nominal factor of safety. Once you have passed this limit state, the strain limit state, then one goes on to investigate the tensile strength limit state. And depending on the geometry of the void, one can then calculate what the maximum tensile strength in the reinforcement is. You can compare that to an available or allowable tensile capacity. And again, that gives you a nominal factor of safety. And then finally, it's important that the reinforcement have sufficient stiffness in order to carry that combination of maximum tensile load and maximum strain. And that defines the stiffness limit state. And we use the symbol J. And this is a new stiffness limit state that came out of our work. We have to make sure that the stiffness of the reinforcement doesn't exceed an available stiffness from a target material. So the question is, how do we get this stiffness? Where does this stiffness come from? Well, not unique to our problem. We developed a model, a two-component hyperbolic isochronous secant stiffness model that has the equation that you see on the right-hand side. And one takes the results of constant load creep tests from the lab. You can develop from these curves, and this is a technique which has been around for a long time, so-called isochronous load strain times for different durations of load. From these curves, one can construct stiffness versus strain curves for different isochronous times or load duration times. And these stiffness curves are well quantified using this hyperbolic model that you see here. So how do we get those parameters in that hyperbolic model, these J and psi terms? Well, we can get these models from product-specific creep testing, or we can get them from correlations that we have developed that I'm going to show you later. So, for example, for a specific product, in this case, a uniaxial HTPE geogrid, you can see the isochronous load strain curves that we developed from these constant load creep tests, and then you see the stiffness curves. And there's also in the legend, you can see the magnitude of those two parameters, J naught and psi, in this figure as well. So you can do this for any product. An alternative way to estimate or calculate what the stiffness is to use some sort of correlation. And what we did is we collected a large database of constant load creep tests, and we were able to correlate the stiffness that you see on the vertical axis of the left-hand figure with the ultimate tensile strength of the reinforcement, which is taken from the results of conventional 10% strain per minute in isolation tests, as you see on the right-hand side of this slide. And what we found was that there was a log linear relationship. I'm sorry, there was a linear relationship between these two parameters. This means that if you know the ultimate strength of your reinforcement, which is a parameter which is readily available, based on our interpretation of the test results, we can estimate what this stiffness parameter will be at 5% strain and 1,000 hours. So here's an example of how one can carry out a design for a particular problem, which the height of the fill to the ratio of the void width is 1.5, and we're designing to a maximum strain in the reinforcement of 5%. So here in this table are the properties, the ultimate strength and stiffness properties of 5 candidate reinforcement materials for this particular problem. And the hyperbolic model parameters are shown here for 1,000 hours and 5% strain. Next, one uses this design chart method, and in this case we're using the British standard, and we enter the top chart again. We have 5% as our target strain, so this tells us what the ratio of the deflection to the width of the void will be, and it satisfies this target maximum strain of 5%, and then we calculate what the maximum load is, and we compare that to the allowable maximum load from our 5 candidate materials. And then we go on to check the stiffness. And you can see in this table that I have at the left, you can see that 4 out of the 5 candidate reinforcement materials satisfy the tensile strength limit state, and 2 out of 5 satisfy the stiffness limit state. So finally, options 4 and 5 will provide adequate capacity for this particular problem. So from this work, we have developed a design chart method for multiple analytical solution types, and these are the Giroux method and the design code methods. But the thing that we added to each one of these methods is a new geosynthetic stiffness limit state in order to fully complete these analytical solutions. And the model that we use to calculate the stiffness is this 2-component hyperbolic isochronous secant stiffness model, which we have also used for other reinforcement applications, like, for example, MSE walls. And we've shown how people can gather this data from product-specific testing or from correlations, for example, with the ultimate strength of these products, which, as I said, is easily available in the literature. So moving on, again, to summarize, we have these different analytical approaches which are available to us. And prior to our starting the research on this topic, this is what was available to us and practitioners. Now, there are disadvantages of these analytical methods. First of all, you have to assume first a reinforcement displacement, vertical reinforcement displacement first, and then the reinforcement deformation profile is assumed in these analytical solutions. And the maximum strain is computed from the deformation shape and vertical deformation. And another disadvantage is the maximum tensile load is assumed to be, the maximum tensile load is computed from maximum strain and force equilibrium, assuming a linear elastic stiffness. I think at this point, you probably agree with me that the stiffness of the reinforcement is not linear elastic. It's a function also of time and strain. And the coupled effects of the soil properties and the reinforcement properties are ignored. And finally, these geosynthetic materials are rate dependent. So all of these factors were not considered up until the time that we got involved. And, it's reasonable to expect, looking at this generic reinforced fill over a fill problem, that as the stiffness of the reinforcement increases, the vertical settlement of the reinforcement and the fill surface will decrease. And of course, we can't model that using analytical solutions. We really have to use some form of numerical modeling. And this introduces the numerical modeling that we have carried out and is described in this presentation. So we carried out a large amount of continuum model testing, if you like, using the finite difference method in 2D FLAC. And this slide here shows an example geometry where you can see that the fill is half a meter in height. So this might be typical of a roadbed. There's a foundation, which in the modeling is only about 1 meter deep, but it doesn't need to be any deeper than that in order to investigate the things that we're interested in. And this void, and this example is 2 meters, but we carried out simulations for voids of half a meter to 5-6 meters or more. So this just gives you an idea of the basic numerical model that we used in our study. However, one must develop first some confidence that your numerical model is going to give reasonable and useful results. So before we launched into this huge numerical modeling program, we found some physical tests at field scale that had been carried out by Villard and Briançon. And what they did is they created at a field site an excavation in a soil foundation. They filled that void with balloons. They placed the reinforcement and the fill on top of it. They also surcharged the surface at intervals. And then they deflated the balloons, and this created the void. And in the photograph at the top right here, you can see the void, and you can see the deflected shape of the reinforcement. And this experiment was monitored with strain gauges, and the deflections were also measured. So what you see on the left-hand side is the white bit here is the void, and the symbols are the measured vertical deflection of the reinforcement at end of construction, I believe. And then the solid lines are our numerical approximation to the measured deflections. And you might agree with me that that's not too bad, the agreement. And then we did the same thing with the strains. And here you can see again the symbols represents the strains in the reinforcement as they span this void, and the solid lines are the numerical approximations or predictions. And you can see that again, we judge the agreement to be quite good. So with confidence in this model, we carried out a parametric study, and we varied the input parameters to this problem. This is including the geometry and the properties of the materials. You can see we used a range of unit weights, friction angles, and cohesion for the fill soil. We looked at a range of geometries with respect to height, width of the void. This gave us a range of height to void width ratios. And then, of course, we looked at the effect of the reinforcement stiffness parameters that you can see here. And in fact, FAHIMA carried out 412 simulation cases. So it's a huge database of, if you like, synthetic data. And in the simulations, we used our 2-component hyperbolic isochronous secant stiffness model. And this model was implemented in flak. And this parameter, actually it's chi, was most responsible for capturing the creepiness, if you like, of these reinforcement materials. So if this material, if this value is very, very high, approaching infinity, then basically our reinforcement is linear elastic. But as it becomes more load and strain dependent, then this value becomes smaller and smaller. And here is an example of some numerical results. What you're looking at is a half width of the void. Okay, so the 0 is the center of the void, and 1 meter in this particular example is the edge of the void. And here we've run a number of simulations where the only thing that was different between each simulation was the stiffness of the reinforcement. And what you can see, that as the reinforcement gets stiffer and stiffer, the deflection at the bottom of the fill surface at the elevation of the reinforcement becomes less and less. And this is in sympathy with our expectations. This slide here is looking at the influence of reinforcement stiffness and void width on tensile load. And what we did in our presentation here is we looked at two different cases. One case on the left is with a relatively low stiffness reinforcement, and on the right, a relatively stiffer reinforcement. Because the problem is symmetrical, we can show two cases at the same time. So what you see here on the right-hand side, you can see that as the stiffness of the as the width of the reinforcement, the width of the void gets larger and larger from 0.5 to 3 meters, you can see that the tensile load in the reinforcement goes up. And I think that makes intuitive sense. But the actual magnitudes are sensitive to whether you have a soft reinforcement versus a stiffer reinforcement. So you can see that the tensile loads are less for the softer or less stiff reinforcement. The other interesting thing you can see here is that the peak tensile loads do not occur always at the center of the reinforcement. As soon as you get above a void, a width of about a meter, you can see that the maximum loads in the reinforcement were actually at the edge. And this is a phenomenon that you cannot capture using an analytical method of the types that I've mentioned earlier. But again, the load is the tensile load is a function of the stiffness of the reinforcement and the void width. So here, again, on the right-hand side, you can see that the loads are highest for the stiffer reinforcement, which is not unexpected because we all know that if you have in structures, if you have a stiff element, it tends to attract the load. And this is the same thing that happens in our problem. Here you see a slide in which we have, again, stiff reinforcement, less stiff reinforcement, but what we have varied here is the ratio of the height of the fill to the width of the void. And it's interesting, you can see that it really doesn't have a major effect on the reinforcement strains. But again, the strains are much higher for the softer cases. And you can see that, again, that the maximum strains are at the edge of the void. And in this particular example, you can see that if one used the more creep-prone reinforcement, then you're going to have strains that exceed the maximum allowable strain of 5%. So this would disqualify these particular reinforcement products because they do not satisfy the strain limit state. Here again, another slide. This is looking at the effect of fill quality. And we ran the same simulations over again, but we increased the compacted fill density from soil type 1 to 2 to 3. And then just for fun, we also looked at a case where we just dumped the fill in place, which you'd never do in real life, but it serves to show trends in the numerical outcomes. So if we focus on well compacted to lower compacted fill cases, 1, 2, 3, you can see that the strain in the reinforcement is increasing as the fill quality goes down, again ignoring the dumped case. And then on the left hand side, we have the same fill but a lower stiffness material, and again you can see that the reinforcement strains are greatest at the edges, and we have situations in which we would not satisfy the 5% strain limit state. So from this work, there was a paper that was published together. You can read this paper and get details. The paper records a number of important conclusions and observations. They're listed here. I'm not going to go through them in detail. Some of them I've mentioned already. You know, for example, that the maximum strains provided we have a reasonable width of void should not exceed 5%. And as the void width increases, we get increasing reinforcement deflection, surface deflection, and maximum reinforcement tensile load and strain. So you can read these this paper at your leisure. But now what I want to do is I want to move to the third part of my presentation, which involves the probabilistic design for the reinforced fill over a void problem. What we're finding in geotechnical engineering and in reinforced soil technologies, of which one is this problem of a reinforced fill over a void problem, is a movement towards design based on probabilistic outcomes, so that we can describe margins of safety in terms of the probability that a limit state is not satisfied. So here we are. We've seen this slide before. Here's our design procedure, if you like, going through these three different limit states, and for each one we can calculate a nominal factor of safety. Okay, nominal factor of safety for the strain, nominal factor of safety for the tensile load, and a nominal factor of safety against not exceeding an available reinforcement stiffness. The question then is, what is the probability when we do this design that nominal factor of safety will not satisfy the target value that we have assumed from simple deterministic analyses? And this is a challenging question, because when you look at each one of these limit state nominal factor equations that you see on the right-hand side, there is uncertainty. There's uncertainty in the magnitude of the computed tensile strain using your formula here for the British standard, or an equivalent formula for any one of the other methods that I introduced before. There's uncertainty in the magnitude of this computed maximum load, And because there's uncertainty in the strain and the load, there must be uncertainty in the mobilized stiffness of the reinforcement. So we have uncertainty in the strength, the stiffness, and this uncertainty can be understood to be due to model accuracy. And this means when we say model accuracy, we can quantify the model accuracy as the ratio of one of these measured quantities, nominal values, and the value that's predicted. Okay, so measured to predicted. If you had a perfect model, then anything you measured would be the same as what you predicted, and therefore the bias value would be equal to 1. This does not happen in geotechnical, reinforcement, soil structure, interaction problems. And also to complicate things is that there is uncertainty in the values of the nominal values that you put into these equations. There's going to be some uncertainty, for example, in the unit weight of the soil. So all of these things conspire to generate uncertainty every time you calculate a nominal factor of safety. It's not a single value outcome. So let me demonstrate for the case of the reinforcement stiffness. Again, the model bias for the calculation of stiffness is the measured or true stiffness value against what you're predicting. If you have, for example, product-specific data, which you often have, like the data can be gathered from tests, from constant load tests that you see here, or stepped isothermal methods. And if you gather that data, the mean of your predicted values and your measured values is about 1. And the spread, the coefficient of variation, is about 6%. If, however, I use this correlation between tensile strength that I showed you before and the stiffness, so that from my nominal value of tensile strength, I estimate what the stiffness is going to be, there's some scatter. And from collecting, data from products from the same product line, the spread is about 20% on your estimate of the stiffness. If you simply take all of the stiffness versus tensile strength data that we were able to collect, and we were able to collect several hundreds of these type of data, and then you just use this overall correlation between ultimate strength and stiffness, then the accuracy in terms of spread, the coefficient of variation, is about almost 30%. Now, this curve on the right-hand side is quite useful, because what it says is that as long as your product falls within the envelope of products that we investigated, you can make an estimate of what the stiffness is without having to actually test the material. So that has some sort of advantage. It's also useful for carrying out parametric analyses. However, the slide shows that there's increasing uncertainty in the estimate of the reinforcement stiffness using this hyperbolic model as you go from product-specific testing to product type data testing to pooled data testing. So there's an argument that says use product-specific data if you have it, because that'll increase your confidence in the estimate of the nominal factor of safety for each one of the limit states that we talked about. So I want to warn you, I'm going to show you an equation that looks pretty scary. And what you see here is a closed form solution. This solution allows you to calculate the reliability index for any one of those three limit states that I've described to you, provided you have the bias statistics and the statistics for the nominal values that you put into your limit state equation. And it's color coded, so the green terms are represent the uncertainty in the input parameters that you use at the time of design. The yellow terms are statistics related to the accuracy of the model, and there can be correlations between model accuracy and the nominal value, so they're in blue. And then you see in this equation the nominal factor of safety. So this is the factor of safety that you would calculate based on your best estimate of the nominal resistance and the nominal load at time of design. This is the old deterministic way of doing things. And it's interesting, you can reformulate this equation, and what you'll see is that the reliability index is log linearly proportional to the nominal factor of safety. As beta gets higher, you have greater safety, probabilistically speaking. And you can see that the nominal factor of safety, as it increases, beta increases. And I think this is consistent, with our intuition. Now, structural engineers use the reliability index routinely in their calibrations, less familiar to geotechnical types, but reliability index and probability of failure are related. They're related mathematically. And what you can see in this figure here, I've simply plotted probability of failure, that is, that we can use, failure not to satisfy our limit state against reliability index. Typical ranges for the probability of failure and reliability index are shown here. So for example, if you want to design for a probability of 1 in 1,000 that your limit state will not be satisfied, that corresponds to a reliability index of about 3, just to put things into perspective. Now, the advantage of this log linear equation that I showed you before is that if we have the statistics for model accuracy and estimates of the statistics for the input parameters, we can calculate reliability index versus nominal factor of safety. And on top of that, I can assign different levels of confidence in the calculation of the normal load, and each one of those conditions will give me a linear line, as you see here. So the coefficient of variation of the nominal load varies here from 10% to 30%. 20% is sort of typical. If you have less confidence, for example, you have less data or quality of data, you might want to use a COV on your nominal load estimate of maybe 30%, which is this line. So here you can see that let's imagine we have typical confidence in our input parameters, which is the middle curve. And I want to satisfy a probability that my tensile strength limit state will not be satisfied of 1 in 1,000 or a reliability index of 3. I just come across until I hit this curve of interest. I go down to the horizontal axis at the bottom, and that tells me that when I do my deterministic analysis, I have to satisfy a nominal factor of safety of 2.4. If, on the other hand, I have less confidence in the in my model or the project conditions, etc., then using the this curve for a low confidence, then I would have to use a higher factor of safety in my design in order to meet the same target probability that the tensile limit state would not be satisfied. And similar curves to this can be constructed for the other two limit states that I showed you before. So based on this portion of my talk, I'd like to, I can summarize by saying that reliability-based design provides a more nuanced appreciation of margins of safety, quantified as the probability that a limit state is not satisfied. In other words, if you design for simply a target factor of safety using nominal values, you know you're safe, but you really don't know how safe you are in terms of probability that your nominal factor of safety is going to be satisfied. Another thing that has come out of this work is that by providing this closed form solution, it means that you can put this equation into a spreadsheet and you can do these types of parametric analyses yourself and create those curves for beta versus nominal factor of safety that I showed you. The other thing that's an important contribution is we have quantified the influence of model accuracy, or what we term model bias. And this is a novel contribution to this particular design problem. The method, by introducing, measures of the confidence in our values of nominal load and nominal resistance at time of design, introduces engineering judgment. A complaint that folks often have is that that when we use probabilistic design, we can't introduce, human uncertainty, but you can do that explicitly here by assuming different levels of confidence in your design and selection of parameters at time of design. And there's a quantitative link between conventional deterministic factor of safety and margins of safety expressed probabilistically, because it has been the case in the past that there are two solitudes. There are people that design using deterministic approaches and those that are promoting probabilistic approaches. But here you can see that we've been able to connect the two together. And finally, the general approach can be used for using whatever your favorite analytical solution approach is, whether you want to use a code approach from the Brits or you want to use the Giroud approach, the methodology remains the same. So the results of all this work, and I've taken this from a bunch of papers, and again, Fahima did all the heavy lifting, and she's a super PhD student. For the professors that are out there, she wrote a manuscript thesis of 5 chapters, and each chapter became a paper in a credible journal, and each one of them won a best paper award. So I think that any of you professors out there, I'm sure, are quite envious. So I thank Fahima again for her good works. And with that, that's the end of my presentation, and I'm more than happy to take some questions.
That was a great presentation, Dr. Richard. I have a couple of questions before we dive into technical things. So you started your career maybe teaching and research way back in 1980. How do you see this field evolved in the past few decades, and what are your insights on that?
Are you talking about this particular application or just in general?
In general, about the geosynthetics field you have been seeing so far in the past decades.
Well, I was very fortunate because when I started as a young academic in the 80s, geosynthetics had just been invented, and so the whole discipline was wide open and provided all sorts of opportunities for researchers, particularly young researchers looking for something to do, to make contributions. And so my interest in geosynthetics started, 40 years ago almost. And fortunately, I've been able to ride a wave and look almost sequentially, at different problems and to improve our methods of analysis for those problems, but all of them having a common component, which are geosynthetics. And this went, using simple analytical methods, for example, for MSE walls, right up to what we're doing now, which is probabilistic design, and also calibration for load and resistance factor design. And I've spoken on these different topics throughout my cross USA lecture tour.
And one more non-technical question. So you have led a lot of professional societies, and you have met a lot of young professionals throughout your career, and also recently during this cross USA lecture. What did you learn from your experiences, and what you would give your advice to young professionals out there?
Well, the first thing I learned was I wish I was young again. The second answer to the second question is I'm quite biased in my belief that the way forward in geotechnical design and the design of soil geosynthetic reinforcement structures is a probabilistic approach, and I think there's lots more work to be done. And so that may be there may be opportunities for the young people that I met to look at this as a research topic, because I know that when you're a young researcher, you're often intimidated by trying to find something new to do, if you like. And so this is some of the advice that I've given people, on a technical basis. I've given them all sorts of other life, advice too. Like don't always aspire to be an academic. I find that a lot of my former PhD students have wonderful careers in industry, including Fahima. She's at WSP right now, Golder, and she's doing lots of interesting stuff. So you don't have to be an academic to do interesting work.
We have first question from Vishnu. He asked, does the 5% strain take into consideration the strain that would cause the fatigue or strain, fatigue stress or strain to an asphalt pavement surface placed below the void?
Actually, is that Vishnu Dialji?
Yeah.
I just want you to know that Vishnu and I went to grad school together almost 45 years ago. I still count him as a friend. So thank you, Vishnu. Yeah, there's you have to be careful, okay, because the strain, that 5% strain that I'm talking about here, is a strain limit that we often adopt to be sure that the reinforcement itself will not strain to rupture in the future. And the strain that is required to keep the deflection, if you look at this slide here, if you're a pavement engineer, you're much more interested in this DS term that you see here. So that is actually another limit state that one has to consider. And this deflection, this level of deflection can easily control your design if you're trying to keep the bump in the road to an acceptable level. And in these papers that we've written, we've also included that as a limit state. I hope that answers Vishnu's question.
So we have one more question from Guru. He is asking, like, the analytical and numerical approaches discussed appear to be 2D, whereas voids are 3D. Yeah. Therefore, how well do they model real life situations?
That's an excellent question. And if you read our papers, what you'll find is that if you design for the void case using the plane strain case that we show here in the slide, so this is assumed to be like a trench. You will have a more conservative design. In other words, a less safe design if you use what I've shown you here. So that means that your void problem won't be quite as bad. The complication that comes from the circular case is that a lot of these most reinforcement products have a strong direction and a relatively weaker direction. The same with stiffness. So what you have to do is what most people do is they overlay them the reinforcement. They put 2 layers of reinforcement or maybe more at crosswise to each other in order not to have a preferred low stiffness direction.
I have one more question. How does this rate dependency in geosynthetic stiffness influence long-term performance over reinforced fills over voids?
Well, what we have done is we've done the calculations using reinforcement stiffness for different assumed durations of time. So, for example, we've taken 1,000 hours. We're assuming a scenario where this void, this bump in your fill, is going to be there for 1,000 hours before you actually fill the void. If the time is shorter, then all of these stiffness values that I've given you, you can calculate what the stiffness of the material will be for shorter durations. So in fact, if the duration between the time the collapse has happened and the time you remediate is 100 hours, well, you'll be able to use a stiffer value in your calculations and therefore achieve, a more effective solution. So we have our designs have as an input the amount of time that the reinforcement has to provide this support function.
Okay. And I have a few more questions here. So now we have seen a lot of instrumentation going on over the payments or anything, right? So what is the most challenging parameter for you as a researcher you think is important? The data we get from the field for designing these, we are not able to capture it.
Yeah, it's very difficult because in a practical real world application, you don't really know where these voids are going to occur, right? You can have miles and miles of roadway, for example. So this is why the only measurements that we were able to find were from a number of carefully carried out field tests like the ones that I showed you from Villard and Briançon. Also, there have been some tests, model tests that have been carried out, and some of that data was of high enough quality that we could also include it in our back analysis of model accuracy. Then the only other way to go is to calibrate a good numerical model against measured data, as we did, and then create synthetic data, as we did, in order to come up with recommendations for the design of these systems.
Thank you, Dr. Richard.
All right. Well, fantastic presentation, Dr. Bathurst. Leela, thank you so much for moderating this live stream. Thank you, everybody, for watching today, and especially for those who stay with us until the end. Thank you for the questions. That's what really put value on these live streams. We really appreciate your contribution, your suggestions, comments, questions. GeoPeer, thank you for sponsoring another live stream. We are more than happy to have you as a sponsor. For all our viewers, again, if you like what you saw, remember to like, subscribe, get notifications. We are very active in our YouTube channel. Our next live stream will be I believe in 2 weeks. And that is the 2024 Raul Peck Lecture by Dr. Jorge Zornberg. That one will be in Spanish. So that's for our speaking Spanish community. So he will be talking about, I'm doing the translation in my head, expansive clays in roads. So if you would like to get notifications about that upcoming live stream, follow us in YouTube or our Eventbrite so you get notifications. Again, if you would like to contribute to the student fund and get your own bobblehead, we have other items, but this is our limit edition. So get yours as soon as possible. Other than that, I hope all our viewers enjoy today's live stream. I would like to say one more time, thank you, Dr. Bathurst. I hope you have a good time being the Cross USA lecturer during this year. I hope our chapters and GSOs had a good time with you. And thank you again for having the time and do this live stream for all our viewers. My last thank you is to GeoPeer. Thanks for sponsoring again the 2024-2025 Cross USA live stream. I would like to start. Let me not start sharing this yet. I need to say something about GeoPeer. GeoPeer is the industry leader in ground improvement. With GeoPeer, you can design and build with confidence, as they provide you with the cost-effective, proven engineering solution that meet your project pricing and schedule objectives. GeoPeer collaborate with you to develop a cost-effective design that allows for higher design, bearing pressure, settlement control, and reduced construction timelines. Celebrating 25 years of project excellence, GeoPeer specializes in rammed aggregate pier, rigid inclusion, slope, reinforcement, and rail subgrade improvement solution. There is no soil type or structure that GeoPeer cannot handle. So thank you so much, everybody. I will now play the GeoPeer video and the next one. All right.